Okay, so let's do the solutions now for the practice exam. So let's first start with this problem here. A child is trying to stack two uniform wooden blocks, 12 centimeter in length, uniform, so from one side to the center of mass is therefore 6 centimeters right in the center, so they will protrude as much as possible over the edge of the table without tipping over as shown in the figure. What is the maximal possible overhang distance D here? So it's that distance here of the top block here. So now let's sketch here roughly the center of mass location and the center of mass location here. So the top block will undoubtedly have a gravitational attraction, a gravitational force downward here. So let me draw this like this here, and let me draw this here like this here. And therefore, if you now consider the top block, let me refer to this as 1 and 2 here. The interaction between block 1 and block 2 here is therefore such that there's a normal force from 2 onto 1. There's, however, also a normal force from 1 onto 2 here. And that normal force, that force from block 1 onto 2 gives rise that there's a downward force onto block 2 here, giving rise to a potential a torque here around this particular point of rotation here. Okay. So now, how far can we push this top block here to the right here? So now there are possible answers shown here: 5 centimeters, 6, 7, 8, and 9. Imagine it would be simply 6 centimeters. Well, then the center of mass of the top block would exactly coincide here with that point of rotation. Let me refer to this as P here. So this is the gravitational force on one, gravitational force on the other one. They are the same in magnitude and same in direction because the masses are the same here. If it would be 5 centimeter, then the center of mass here of the top block would be to the left of this point of rotation. If it's 6 centimeter, would be exactly coinciding with that. So can we push this a little bit further? 7, 8, and 9. Well, if it would be in fact 9 centimeter, well, then what would we have here? Then we would have a symmetric configuration here. Namely, let me sketch this like this here. So this here is 6 centimeter. This here is 6 centimeter. This here is 6 centimeter. And this here is 6 centimeters. So now the torque contributions onto block 2 here will cancel each other. If that distance here from the gravitational force on block 2 relative to point P and from the gravitational force on block 1 relative to point P is exactly the same. So then the torques as a torque sum cancel each other. And this is exactly then the case when they are when D is exactly 9 centimeters. So this distance here is 6. This distance here, this would be 3 here. So this is 6 here, 9, this is 3 here. And here then this is also exactly 3 centimeter here. So 3 times the gravitational force on the right hand side and 3 times the gravitational force on the left hand side just exactly balance each other. So it is indeed answer E here. So now a heavy boy and a lightweight girl are balanced on a massless seesaw if they both move forward so that they are 1/2 their original distance from the pivot point. So the idea is that they both move forward so that they are 1/2 their original distance from the pivot point. What will happen to the seesaw? Assume that both people are small enough compared to the length of the seesaw to be thought of as point masses. So imagine you refer to the first one has a distance d1, and the respective force, gravitational force, would be F1, and that is in balance to the other child d2 times F2. So undoubtedly, heavy boy, lightweight girl, they have two different gravitational forces, and therefore if the torque in magnitude have to be the same, so then d1 and d2 is different. So now if we go to half the distance, half d1 here times F1, and half d2 times F2, namely the respective torque, calculating this for the lightweight girl. So let's say this is the girl here and this is the boy here. Then you see here then the torque from the girl is a half d2 F2, and from the boy it's a half d1 F1. But that is exactly the same thing, since d1 F1 and d2 F2 is the same. We simply multiply this equation by 1/2. So nothing will happen. So it's answer D here. Then let's come to the gravitational force, planetary motion problem. A satellite in circular orbit of radius capital R around planet X has an orbital period T. If planet X had 1/4 as much mass, the orbital period of this satellite in the orbit of the same radius would be. So now let's write down here the gravitational. So let's start with second Newton law here, and then along the unit vector r direction. So what would we have here? We would have here minus g, capital M, the central mass, the mass of the satellite, divided by r squared, and that equals to minus the mass of the satellite times omega squared times r. So now you can solve this for, replace omega as 2 pi over the period. And then what do we find? Then we have here g, the mass of the satellite cancels out. Then we have here m divided by, and you can divide out r, so it's r to the power of 3 equals to 2 pi squared divided by t squared. So let's solve this now for t. And then we have here 2 pi. So you multiply this by t squared, take the square root, and then you have 2 pi. And then we have on the other side, we have r to the power of 3 divided by g m, and the whole thing to the power of 1/2. So now if we're going from m to, what does it say now? If planet had 1/4 as much mass, from m to 1/4 m, then you see exactly what will happen here. So you replace here m by quarter m here. So you multiply by the inverse, then you have 4 divided by m, and take the square root of that, and then you have a factor 2 compared to the original. So therefore, it is answer B here, 2t. Then similar problem, planets Z34 has a mass equal to 1/3 that of Earth, a radius equal to 1/3 that of Earth, and an axial spin rate at 1/2 that of Earth. With g representing as usual the acceleration due to gravity on the surface of Earth, the acceleration due to gravity on the surface of Z34 would be. Well, so first of all, what is relevant here right now is minus g, m, the mass of an object here, mo divided by r squared, equals to minus the mass of the object times g, Z34. The mass is independent on that, so therefore we have then G34 equals to capital G m divided by r squared. So now if we're now going over to a system where, so we have g, but now we're going over to 1/3 of the mass, so m we're dividing by 3, and then the radius goes also to 1/3 of that. So we have here r squared times 9 So this would be then 3gm divided by r squared. And so therefore it's a factor 3. So the spin rate which is mentioned here does not really enter in this problem. As you're leaving a building, the door opens outward. If the hinges on the door are on your right, what is the direction of the angular momentum of the door as you open it with respect to the hinges as the total rotational axis? So let's imagine you have a door here like this. And let's say this is this side is the hinges here on your right hand side. Here's the doorknob, and that door would swing outward here. So now use your right hand. The thumb is pointing downward here. Your four fingers here curl in the direction of that of the rotation. So your thumb is pointing downward here, so the angular momentum would point downward here. Suppose an ice skater has a moment of inertia I1 while spinning with arms wide open, and I2 if she closes her arms. If she has an angular velocity omega 1 with arms open, what angular velocity omega will she have with closing her arms? So angular momentum equals to L times I times omega in magnitude. Angular momentum is conserved, so therefore L1 equals to L2. So I1 times omega 1 equals to I2 times omega 2, and therefore omega 2 equals to I1 divided by I2 times omega 1. A simple spring mass system of mass m and spring constant k is performing harmonic oscillation without friction in the horizontal direction. Determine the period of t. So we apply here second Newton law. This is the unit vector I direction. So you have here, let's say, a wall here. This is the horizontal surface and no friction. Here's a mass, and here's an object of mass m, spring constant k here. And here, this would be the equilibrium location, x equals to 0. So now there's a restoring force acting on the system in the opposite direction. So this is the unit vector direction I here. So this would be minus kx equals to minus m. And then I write this already as the second derivative, d squared x dt squared. And write the derivative also as minus mx double dot with that notation of the second derivative in time. So then we have here, if you solve this then for x double dot plus k over m times x. All right, so how do we come now to the period? We use the solution function x of t as the amplitude times cosine omega t, and therefore the second derivative is minus a omega squared times cosine omega t. And if you insert now x of t in here, so x of t in here and x double dot in here, then you can cancel out a and cosine omega t here, and then what do we find? We have then minus omega squared, so namely from this side here, and plus k over m equals to 0. So therefore omega squared is k over m, and omega, as writing this as 2 pi over t, then t equals to 2 pi in the square root of m divided by k in the square root of that. So now a traveling wave is described by y of x of t equals to 6 cosine 6x plus at. Determine the wave speed. All right, so now let's go back to our discussion in class. Kx plus omega t, so therefore k, the wave number, is therefore 16 1 over meter. Is another different way of formulating wavelength. and omega is nothing else than 8/1/2. So now v, the wave speed, is lambda times f, or omega divided by k. And so therefore we can write this as 8/16, and the respective unit is then meters per second, so it's 0.5 meters per second. And last but not least, the large piston of a hydraulic lift has a radius R2. What is the force F1 which has to be applied in the small piston to lift a car of mass M placed on the top of the large piston? So the idea here is that pressure is the same in this hydraulic press. So P1 would be now the force F1 to be applied divided by the area of the circular piston, pi R1 squared, equals to, and now you have here F2 divided by pi R2 squared. However, F2 equals to mg, the mass of the car, times g, divided by pi R2 squared. And now you can solve this for F1, and therefore have R1 over R2 squared times mg. Okay, so let's now, let me just pause here for a moment, and then we do the analytical problems. Okay, so let's work now on the first analytical problem. A pulley of mass MP, radius r, and a moment of inertia about the center of mass, which is given as a half mpr squared, suspended from a ceiling. An inextensible string of negligible mass is wrapped around the pulley and attached on one end to an object of mass m1 and on the other end to an object of mass m2, with m1 larger than m2. At time t equals to 0, the objects are released from rest. So sketch a free body diagram for both masses along with the choice of a coordinate system. So let's work on this. All right, so this here is now problem 1. All right, so this is part A. So a free body diagram. So here, just for the two masses, this is mass m1 here. Let's draw here the two forces, so the gravitational force. So this here is m1g, and then the tension in the string, T1. And then we have the same thing now for mass m2. Same type of forces, gravitational force, m2g, and the tension in the string. Okay. So now let's go back here. It said in the problem, assume that m1 is larger than m2. At time t equals 0, the objects are released from rest. So therefore m1 will go down while m2 is going up here. So that pulley is rotating then counterclockwise. So let's go back here. So therefore, since m1 is going down, we place the positive direction downward here. So therefore, analyzing m1, so this is j, here unit vector j, whereas we place the positive direction for m2 upward here. Okay, so I think that was basically already it as far as part A is concerned. Now part B, sketch a torque diagram for the pulley, meaning the torque location and force vectors along with the proper choice of coordinate system. So now we have to work on this a little bit here. So now let's come to part B. Okay, so now let's draw here a circle here. Okay. So here the center here, and let's now focus on all forces acting on that. So well, oops, the string is wrapped around here. So here's the attention in the string here now downward here. So this is T1. And here is now T2 here. And therefore we can draw here now the location vectors from the point of rotation to T1, R1, and from the point of rotation to T2. So this is R2 here. So this is now all very well defined. So now let me draw here clearly the directions. So this system is rotating here now counterclockwise. So now let's come to the choice of a coordinate system. So now let's place the positive direction of the tangential vector, which we denote as t hat or theta hat, in the direction of this counterclockwise rotation. So therefore, theta hat is downward here. And I draw this here for that particular occasion. This is a coordinate system, unit vector basis system, which travels along with every point. The radial unit vector is therefore outward. And now evaluate r cross theta is therefore k. So therefore r, use your right hand r, point your thumb in the direction of r, your pointing finger downward in the direction of theta hat. So then k is coming out of the plane here, out of the screen. So k, oops, would be therefore coming out of the plane here. So this is here now k. So k hat is coming out of the plane with our usual convention. And what I strongly encourage you to do now is to draw that coordinate system, since it travels along with the object here, to sketch this coordinate system now here also for the other point where we have to then formulate the respective vectorial quantities. So now the tangential vector theta hat is in the direction of the rotation upward here. Radial unit vector is outward here, r hat. So therefore r, theta, and k as expected is coming out of the plane here. So here's k hat here. All right. So this is now a complete torque diagram. Let's go back here to sketch a torque diagram for the pulley, meaning the torque location and force vectors along with proper choice of coordinate system. Before we come now to part C, let's formulate right away all of these vectorial quantities here right now. So what do we have then? We have then R1, we need to formulate R2, and we need to formulate T1, and we need to formulate T2 here with this unit vector basis. So what do we have now? R1, well, the radius of that pulley is capital R, so the magnitude is in both cases R. Radial unit vector, let's work on R1, is pointing radially outward here, so it's clearly R hat. Let's jump now to R2 here, in the direction of the radial unit vector here, also R hat. And that's why really make sure that you draw this unit vector system here, not only in this direction, but also show it here on that side. Not that you're confused. If you would not draw it here, that you write down R2 is actually capital R minus R. But that refers to that particular occasion. So keep in mind that this polar coordinate system, well, specifically here it's actually cylindrical coordinates r, theta, and k, is really traveling along with a point mass, a point on the circumference here. All right, so let's go back now to T1. So this would be now magnitude T1 here in the direction of theta. So this is plus theta then. Whereas on the other side, T2 is in the opposite direction to theta. So this would be minus T2 times theta. All right, so now let's come to part C here. And let's read again the problem. And it said, formulate second Newton law for both mass and the dynamical equation for the rotation of the pulley. All right, so now let's do this. So F1 equals to M1 times A, and F2 equals to M2 times A. So let's do this right now. So what do we therefore have? We have unit vector j in both directions, two independent systems. So t1 is in the opposite direction, so it's minus t1 plus m1g equals to m1a. As a constraint, both of these accelerations a1 and a2 are the same. And then for the second object, m2 is in the g is in the opposite direction, t2 is in the direction to j. So we have then t2 minus m2g equals to m2a. So let me rewrite this a little bit right now. So we have then m1g minus t equals to m1a. And here we have m minus m2g plus t2 equals to m2a. So let's call this equation 1, equation 2 here. So now we come to the torque equation here. So first of all, let's calculate the total torque. We have two torque contributions. So one from T1 R1 and one from T2 R2. So torque is R cross F. So here we have R1 cross T1 plus R2 cross T2. Now we can replace these vectors. So we have then R hat cross, and really that's why make sure that you formulate these vectors beforehand really clearly using your unit vectors. Now it's just a matter of replacing these vectors in your formulation as unit vectors. So now T1 is there for T1 theta hat. So then we have here T1 theta hat plus, and now R2 is R theta hat cross, and T2 is minus T2 theta hat. All right. So now we can work this out. So then let's separate now scalar quantities in the unit vectors. So then we have here R T1 R hat cross theta hat minus, so R minus T2, let's take this out, minus T2, and then we have left here R hat cross theta hat, which is k. So now you can take this all out. The common factor is k hat and r, so then we have here minus r T1 minus T2 times k hat. All right, so now this is very simple now to formulate the dynamic equation. Torque equals to the moment of inertia around the center of mass times alpha, the angular acceleration. So now we analyze, please keep in mind this is a vector equation here in the k hat direction. So then we have here minus r T1 minus T2 equals to I, let's leave this like that, times alpha equals to I times A over R. But now let's what's the direction of alpha here? Let's be very clear about this. Initially this disk was at rest here, so this disk was not rotating. Now it starts to rotate out of zero angular velocity here, so you have an acceleration which is now pointing out of the plane here. So using your right hand rule here. So now let's denote this here as equation 3 here. And then we simply replace now T1 and T2 here with these expressions from equation 1 and 2 here. So let's do this. So what do we have then here? So if I multiply this out here right now. Oh, I see I have here made here a mistake, RT1 minus RT2. So this is actually RT1 minus T2. I have here a minus sign. So forget that. So that this is corrected here now. So then we have here R T1 minus R T2 equals to I times A divided by R. So let's replace now R with T1. And T1 is therefore M1G minus M1A. So this is M1G minus M1A minus R. And T2 is therefore now M2A plus M2G. M2A plus M2G equals to, and then we have I here divided by R times A. So now we can bring all of the quantities relative to A to the left-hand side. So what would we have then here? A to one side. We have then the term from the moment of inertia, I over R. So this is from here. Then we have here a term and then let's actually first divide out the equation by R. So then we have here actually on the right hand side R squared. We get rid of these factors R here. And then we have here plus M1 and here plus M2 if we bring it to the other side. So we have plus M1 plus M2 equals to, and then what we have left here is M1G minus M2G. And then you can easily solve for this. A is equals to M1 minus M2 times G divided by I over R squared plus M1 plus M2. All right, so this here is now the solution for the acceleration here. Okay, and then you can insert this to determine the tension in the string. Let's go back here. What we calculate the acceleration for both masses and calculate the tension in the string for mass M2 here. So let's solve this now for T2 here. So this is then part D here. Just go back here. Actually, this was part E is the tension in the string. So this here is actually E here. And this here, this was in fact part D here. Let me just move this all down here a little bit here. So this here was in fact part D here. And part C was this part here, setting up the equation of motion. So T2 here is therefore M2A plus M2G. Oops. So T2 is M2A plus M2G. So it's M2A plus M2G. And then you can insert this back into here. T2 is therefore M2. And then M1 minus M2G. And then you have here in the new denominator I over R squared plus the sum of both masses, M1 and M2, plus M2G. You don't have to get hung up to simplify this even further, just leave it like that. That's fine. Okay, so this is was the first problem now. So let me just walk you through a couple of things here, just to remind you of a couple of things. I hope this here is really clear, setting up the free body diagram for mass M1, mass M2 here. here for the rotating object, make very clear at which point on the rigid body that force T1 is actually applied. The same thing here now for T2. Draw then really explicitly from your chosen point of rotation the respective location vectors. And then choose a coordinate system, a polar coordinate system. The tangential director, put it in the direction of the rotation. Our unit vector r is pointing radially outward, therefore k hat is coming out of the plane here. And you can also see the consistency, therefore, with curl your forefingers in the direction of your rotation, then your thumb is coming out of the plane. Formulate then your vectors in terms of this unit vector basis. And then you can set up the dynamic equation for translation here first of the two objects, and then the rotation dynamical equation after you first explicitly calculate the torque, and then evaluate the unknowns A, T2, and you could also do T1. But let me just remind you, you have actually three unknowns here, T1, T2, and A, but we have three equations, 1, 2, and 3. So that's the name of the game. So my hint for the final exam is be very careful and think a little bit about where's the point of rotation, and where do your forces are applied on that rotating object, and relative to that chosen point of rotation, draw your location vectors, choose your unit vector base, and formulate your vectors, and then you will be just fine. Okay, so let's now come to the second problem. Okay, so the second problem, let's read this first. A geostationary satellite orbits the Earth on a circular orbit with the same period as the period Earth period TE. The known mass of the Earth is ME, and the mass of the satellite is MS. The known Earth radius is RE. Sketch a free body diagram considering only the Earth and satellite system along with a proper choice of coordinate system. All right, so let's first do this. All right, so now you have here the Earth, mass ME here, Earth radius, so that's here is the Earth. And then you have here the altitude, really relative to the surface. And let's say the satellite would be here. This is the satellite MS, and the force vector acting on the satellite is just the gravitational attraction from the Earth onto the satellite FG here. Proper unit vector direction here. Radial unit vector r hat pointing radially outward. So now, r is now h plus re. So let's now set up the second part here. So formulate second Newton law. So very simple now. We've done this a few times in class. So F equals to ma. It's a simple circular motion problem. So now, what do we have? We have minus g. You have seen this in one of the concept questions before. Mass of the Earth, mass of the satellite, divided by r squared equals to minus m mass of the satellite times omega squared times r. And now omega equals to 2 pi divided by the period t, the known period t. So that's basically it here. So that's was part B, what you were asked to set up formulate second Newton law. So now let's go back what we were asking part C. Determine the height of the geostationary satellite above the Earth's surface as a function of the universal gravitational constant g, m(e), t, and the Earth radius. So now, the height is therefore h equals to r minus re. So keep in mind that r here in the universal gravitational law is really meant center to center. So we can solve this now here for this equation when we're setting up second Newton law to r. So let's divide out here r, or multiply this by r squared, then you get here r to the power of 3 here. And then we have on the other side capital G, we have the mass of the Earth. And then we have here replace omega by 2 pi over t. So then you have here te squared divided by 4 pi squared. Because omega is 2 pi over t, but we're multiplying now t and divide by 2 pi and the whole thing's squared. So therefore r equals to g me times te squared divided by 4 pi squared and the whole thing to the power of 1/3 here. So this would be then therefore h equals to g, so this expression here, g, and then minus re here. So that's the final result here. Okay. And then part D. Let's go back, read part D. Determine the orbital velocity of the satellite in terms of me and then the universal gravitational constant g and te. All right, so now let's see. We have to bring now the orbital velocity into the game now here. So instead of writing here the left-hand side of the applying second Newton law, we leave like that, g, me, ms over r squared. But the right-hand side, we're introducing here now the orbital velocity. And that's, so this is therefore minus ms v squared over r. Remember, the omega is equals to v, the linear velocity, over r. You're dividing out the radial dependence. So therefore, let me rewrite this. We have then minus g me, the mass of the satellite, divided by r squared, equals to minus the mass of the satellite times v squared divided by r. And now you can cancel out the mass of the satellite, and you can solve this therefore now for r. And we have then r, so you multiply both sides by r here, or multiply by r squared. So then we have r is therefore g me divided by v squared. Okay, so we need that. So, but now let's look at something. How can we now connect the velocity together with the orbital period. So we have just formulated r now as capital G me over v squared, but we also know that r to the power of 3, or we have actually written here r by itself. So these two expressions are identical, and therefore we can now relate a period in the orbital velocity here. So let's do this. So we therefore have from here, so this expression equals to this expression, so we therefore have G me divided by v squared equals to G me te squared divided by, divided by 4 pi squared, and the whole thing to the power of 1/3. So now to solve this, we take this to the power of 3, and this whole thing to the power of 3 on both sides. So what do we therefore find? We have therefore G to the power of 3, me to the power of 3, v to the power of 6 equals to G me te squared divided by 4 pi squared. Okay. And now we can simplify this a little bit and to solve for v. So g against 1g here gives you an exponent 2 here, me against here gives you an exponent 2 here, and I think that's it then. So now we can therefore write down v to the power of 6 is therefore. So now you multiply this by 4 pi squared, so you get 2 pi squared divided by te squared. So from here, then we have these two terms, and then we have on the other side still g squared times me squared. And now you take on both sides, take this to the power of 1/6, and then you see what you have here. 2 divided by 6 is 1/3, so we therefore have v equals to 2 pi divided by te times g times me, and the whole expression to the power of 1/3. All right. Okay, all right, so that was this. And then the last part is now part E. So what does it say now in part E? How would the radius in orbital velocity change if the period of another stellar would be a factor 4 larger than that of a geostationary? If the period of another satellite would be a factor 4 larger than that of a geostationary satellite. So now we go from TE to 4TE. So what would be now different? So let's first go back to our relation for R. So that's shown here. We copy this. So what would we have now? So we have then now R, and we replace this now by by 4te. So 4te, you have in here 4te squared, so 4te and the whole thing squared would be therefore 16t te squared. So therefore there's a factor 16 to the power of 1/3 involved, larger, by this particular factor for r. And for the velocity, so where's the velocity? We just had that here. So let's copy this here as well. Then what would we have here? Well, in this case, we would not have here t, but we would have here 4te. 4te. So then the velocity would be smaller by a factor 1/4 to the power of 1/3. So 1 divided by 4 to the power of 1/3 smaller. Okay. All right. Let me remind you of a couple of additional aspects concerning planetary motion. Namely, angular momentum is defined as r cross p, or r cross m times the velocity. So imagine you have a circle here, circular orbit. Then what's the relation between r and the velocity at any moment? So this here is r, the velocity is here v, r. So at any point on that circular orbit, r and v are perpendicular, so the magnitude of L would be always r m v. And that is a constant. Why? Well, for central forces, so we have torque equals to r cross f, irrespective if it's now a circular orbit or an elliptical orbit, which I will come back to in a second here. And here's the central system. At any instant, the respective force onto the center from an orbiting system is always directed towards the center. So you can always write r as r times r hat cross, and the force is always written as minus g m of the central system, the orbiting system mass of the central system divided by r squared times r hat. And these are two antiparallel vectors, which is in fact 0, the null vector here. So therefore, since torque equals to dl dt, the angular momentum, and this is therefore 0, so therefore you conclude that L as a vectorial quantity is conserved. Okay, so now imagine now if I'm telling you take an take two extreme points here, point 1 here and point 2 here, then even here in this orbiting system, that planet is going around this way, then the relation between the location vector at this particular point 1 and the velocity vector here is such that they are perpendicular. And also here, the location vector here and the velocity vector are perpendicular. So also in this case, in magnitude, it is rmv. And both of these angular velocities here at point 1 and point 2 would be the same. So you can relate, therefore, r and velocity at point 2 to r and velocity at point 1. Another important relation and realization is the conservation of mechanical energy, the sum of kinetic energy plus potential energy. So meaning a half mv square for the kinetic energy of the orbiting system at point 1, plus the potential energy, which is minus g capital M, the mass of the orbiting system, divided by r, the magnitude, so in this case r1, would be equals to the kinetic energy and the potential energy at point 2 here. So keep this in the back of your mind. All right, so now one last problem. So this is a crane is configured as below, with a beam suspended at 2 points L1 and L2 by the two ends of a cable passing over a frictionless pulley. The two ends of the cable both make an angle theta with the beam, and a counterbalance object A with mass MA is fixed at one end of the beam. A balance object B of mass MB is attached to the beam, so this is shown here, at an unknown location, so that distance is unknown from the counterbalance and can move horizontally in order to maintain static equilibrium. The crane lifts an object, this is the object here, with mass MC at a distance LC from the counterbalance. Now, draw a free body diagram along with a choice of coordinate system, make a choice of point of rotation, and draw for each force the respective location vector. Formulate all location vectors and forces in terms of these unit vectors using the chosen coordinate system in part B. So let's prepare all of this here first. All right, so this here is now problem 3. So this is your beam here. This is your point of rotation chosen. Let's go back to the labels here. So this was A, B, and C. Okay. All right. So then we have here. Let's label this as FA. Then we have here somewhere FB, and we have here somewhere FC here. And then we have here that pulley system from here to here and from here to here. So there are now two tensions here, T1 and T2. The angles are denoted here as theta. So T1 and T2, just by symmetry, are in fact identical in magnitude. Okay, so now let's draw the respective location vectors. So now we have to draw from P. This is R1, R2, this is RB, and last but not least from here, this here is RC. Okay. All right, then the coordinate system, this should be hopefully pretty clear. Cartesian coordinates, I, J, and K is coming out of the plane, I, J, K. All right, so now this is all done here now. And then let's formulate all of these vectors. So then we have FA we need to do. Oops. T1, T2, FB, and FC, together with R1, R2, RB, and RC. All right. So here this would be MA minus MAG times J. T1 is T1 cosine theta plus T1 sine theta j. T2 has a negative component for the x direction, minus T2 cosine theta plus T2 sine theta j. And then FB is minus BGJ, and FC is minus MCG times J. So now for R1 we have L1I, L2I, LBI, and LCI. So now we can formulate the conditions of static equilibrium here. So then we have here F net and the torque. All right. So let's do this first for I and J. So along I, there are only these two here. So this is T1 cosine theta minus T2 cosine theta equals to 0. And from that you can immediately see that T1 equals to T2. All right, so T1 equals to T2 here. Let's call this then therefore T, common symbol. And here the sum of all forces along J, this is minus MAG plus T1 sine theta plus T2 sine theta minus MBG minus MCG equals to 0. And therefore you can solve this now for T, because T is the same, so you have 2T sine theta, and you bring all the mass terms to the other side. So therefore you have then T equals to G MA plus MB plus MC divided by 2 sine theta. Okay, all right, so this is, we're done with this now. So now we have, let me just go back and read part D, formulate the conditions for the above using the identity and magnitude. We actually showed this already in part D, and determine the unknown distance. So now we have to do a little bit of work here. So now we have to calculate all torques. So this is a bit of work now. So the torque has now 4 contributions. 1, so from T1, T2, FB, and FC. But we have all of the vectorial quantities, so this shouldn't be that difficult. So this is R1 cross T1 plus R2 cross T2 plus RB cross FB plus RC cross FC. All right, so now let me replace all of these, and then what do we find? So, so R1, this is L1 I, and then T1, this is T sine theta J, so then therefore we have I cross J, so this L1 T sine theta I cross J, so that's the first term, plus similarly L2 T sine theta I cross j. And then we have the two terms in the other direction. So minus sine minus LB MB G, but R has I and F has J, so it's I cross J, so it's therefore K can rewrite this like this right away, minus LC MC G K. And all of this has to be equals to 0. Okay, so static case requires now tau equals to 0. So therefore, and this here is K, and this here is K. So this is only then fulfilled if now the scalar sum in the K direction is 0. So therefore we have T sine theta. We have here L1 plus L2. So this is from, so we have L1 from here, L2 from here, T sine theta, you can take this out here. And then we have these two negative terms, minus G LB MB minus G LC MC equals to 0. And then you can solve this now for LB. This is then T sine theta L1 plus L2 minus G LC MC divided by MBG. And then we can replace now T from here. So this would be then so let me just rewrite this expression here, then you can see this is a little bit easier to see. So we need this expression here right now. So let's insert this back into here. So now you see here that this sine theta against this sine theta term cancels out here. So then we have here 1 divided by MBG L1 plus L2 and then we have here a factor of 1/2, and then that mass sum M1 MA plus MB plus MC, and then at the end we have here minus LCMC over MB, minus LC, sorry, not write this like this here, minus LC MC over MB. So let's go a little bit slower here. Minus G LC over MC divided by MBG. G goes out, is therefore minus LC times the ratio of MC over MB. And then you can simplify this a little bit still here. So this would be then LB. So now let's see. You can multiply now these mass ratios into here. So you have MBG, G cancels out here, so you can reduce this here, and you can bring MB into the expression. So you have ratios of MA over MB and plus 1 plus MC over MB, and then here LC MC over MB. So we have then a factor 1/2 here. We have L1 plus L2. This is that sum here, that factor 1/2, L1 plus L2. And then we multiply 1 over MB into this expression. So then we have 1 plus MA over MB plus MC over MB minus LC times MC over MB. Okay. All right, I think that's it. So my hint for the final exam, look through the static equilibrium problems that we did in class. Then the ladder problems in your homework problems, look at some of the ladder problems. Ladder problem, you know, where you with or without friction, and then think about how you stabilize a ladder, things like that. Just practice this a little bit. I think this is basically it. Okay.